Welcome back to Calculus 2. We're going to finish up our initial discussion on power series by talking about the effect of some operations on power series. I'm going to, in the midst of it, point out a very important consequence of some of the things we've been doing with them. So we're going to start off with the series multiplication theorem for power series. This says that if you have two power series, a of x and b of x equals this. Notice they're using function notation here. We haven't actually seen the work for it. We're going to see that in a later theorem, but it is true that power series will define a function on their interval of convergence. It's an interesting property of them. They fit all the properties of functions. Every input has a single output. Anyway, so if you have two power series that converge absolutely on some radius of convergence, then this C sub n is the series, basically, of all their multiplications of the coefficients. Then the series of C sub n x to the n converges absolutely to a of x, b of x, for x less than r. So basically the limit of a times the limit of b, the sum of a times the sum of b. So if you multiply two series, their result will be the multiplication of their sums. It's a neat rule. We didn't have it back in the initial properties of sums. We're not going to prove this. It's not proved in the book either, but it is an interesting result. I will say the hard part in doing this is calculating this. Because just think about calculating a finite number of these things. If you're multiplying say a finite series like 1 plus x squared plus x cubed plus 3x to the fourth plus 5x to the fifth, and you multiply times another one that's also 5 terms long, like negative 2 plus 7x minus 8x squared plus 4x to the fourth minus 5x to the fifth. Apparently I skipped the x term on that one. Notice in multiplying these, you'd have so many combination terms. So many of them. And so many like terms you'd have to combine. I mean, just multiplying a 5 term times a 5 term, you get 25 terms that you'd have to combine down. Well, it's the same idea here. The C sub n's would be the coefficients on each term. For C sub 0, it's pretty simple, because it would just be a sub 0, b sub 0, just literally the constant times the constant. But once you start getting up till the second, third, fourth terms, you just get more and more values you have to figure out. It's a nice formula in that it gives you one, but it can just be really tedious to work it all out. If you're using this to do calculations on higher order functions, you need a lot of computing power to do it. So this is a really important theorem. It says if you have a convergent power series that converges absolutely for x less than r, then you can actually compose a function in for the variable, for the x, and it will converge absolutely for any f of x less than r. So you can just plug the function into its requirement and see where that converges. And you can find a new interval of convergence or radius of convergence using that. It's a really neat process. This was something we could do with functions and their limits, even going back to chapter 2. The other things you can do, you can differentiate a series, a power series, term by term. So if you have a radius of convergence that is some finite number, well, it has some radius of convergence greater than 0, it could be infinite, then on that interval has derivatives of all orders, and you can just differentiate them. This is actually a pretty natural result, just thinking about how the power rule works, because if you have a bunch of terms that are just x minus some number to the n with a constant out front, well, all that's going to happen is that their power is going to come down and their powers are going to decrease by 1. And eventually, if you take enough derivatives, if you have a finite number of terms, they'll all go to 0, because eventually they'll all be constants, x minus 4 to the 1, and you take derivative of a constant, it just goes to 0. And just like you can differentiate term by term, you can see, you bring down the power, n, cn, x minus a, n minus 1. Second derivative, n times n minus 1 times x minus a, n minus 2. You might ask, is there a formula for this? I mean, it's basically just n factorial. It's whatever this is, really. Let's see, I guess it would be n factorial over c factorial? I don't know. I have to think about that, because the derivative actually makes a difference here. It's like n factorial over n minus whatever the derivative is. So like if this is kth derivative, then I believe it would be n factorial over n minus k factorial times c sub n x minus a to the n minus k. So for the first derivative, I think that's what it would come out to be. Second derivative, and so on. I think that would actually be the kth derivative formula. F sub k, f kth derivative of x would be that in this case. Each of the derivatives are going to converge at the same old radius of convergence. And just like we have a term-by-term differential, just like we can take derivatives term by term, we can also take integrals term by term. And you increase by 1, divide by it, so n plus 1, divide by it, constant still out front. So you could probably come up with a similar formula for that, doing that. I don't often think about the second integral. That's a little bit of a notation problem. I'm not sure how you would denote multiple integrals other than by just writing indefinite integral signs multiple times. There probably is one for an indefinite number of indefinite integrals. But, I mean, it's still, you just integrate it term by term. That's all of our theories. Let's do some problems. This is going to be a shorter video than the last one, I think. Famous last words, but we'll see. So use the continuous function theorem, that was the first theorem we looked at, for power series to find this, the second theorem we looked at, to find the series interval of convergence, and within this interval the sum of the series as a function of x. Well, the trick with this is a geometric series, because you can rewrite it as, let's see, x plus 1 squared over 9 to the n. Sum n equals 0 to infinity. And we know if you have a geometric series, a common ratio raised to the nth power, on its radius of convergence is going to equal, let's see, it's a over 1 minus r. In this case, a is 1, and this is r. So this is 1 over 1 minus x plus 1 squared over 9. So this is going to be, let's see, multiply top and bottom by 9. 9 over 9 minus x plus 1 squared. Honestly, that's probably fine. This will converge for absolute value of the radius. Let's see. Geometric series converge for absolute value of the radius less than 1. Or absolute value of the ratio less than 1. And the ratio in this case is that. So that's x plus 1 squared over 9 has to be less than 1. Multiply both sides by 9. X plus 1 squared in absolute value has to be less than 9. Square root both sides. X plus 1 in absolute value has to be less than 3. So then the radius of convergence is 3. And it will converge. Let's see. Subtract the 1 from everything. Negative 4 less than x less than 2. And I suppose we ought to check the ends. If you plug in 2, get 3 squared over 9, you get 1 to the n. Yeah, that's... If you plug in negative 4, you get the same thing, 1 to the n. And 1 to the n converges to 1, not 0, so it'll diverge. So negative 4 to 2 is the interval of convergence. And it was legal to do that because x plus 1 squared over 9 is a continuous function. Alright, I believe this will be our last problem for the section. So, this series, e to the x equals 1 plus x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, x to the 5th over 5 factorial, converges to e to the x for all x. It's an interesting thing that you can express e to the x as a power series. And I think this is actually one of the simplest computational ways of actually calculating a pretty exact value of e, is just to do this. Because every time you add on, I mean, 5 factorial, the factorials are going to win, so this is going to be a tinier and tinier value. Smaller and smaller points of accuracy are added as you go, so you can get to a fairly high accuracy by just going a certain number of terms. Find a series for the derivative of e to the x. That's easy enough. You just term by term differentiate. So d dx of 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. I'm tempted to actually do a little work here. You know, that's just x to the n, the sum n equals 0 to infinity of x to the n over n factorial, because 0 factorial is 1. So, just doing that, I mean, you can tell this derivative is 0, 1, bring down the 2, it cancels out, you just get x. Bring down the 3, it cancels out, you get x squared over 2, or 2 factorial. X, bring down the 4, it cancels out, so you just get x cubed over 3 factorial, plus x to the 4th over 4 factorial. And you can actually see doing the work here, if you take a term by term derivative, you'll just get x to the n minus 1. Over n minus 1 factorial. But note you'd lose a term as well, so you don't need to go up from 0 anymore. You go from 1 to infinity. But this is the exact same series as that. So we do get the same series for e to the x, and we can tell just from looking at the general term. The first term went away, so I'm not even really looking at it anymore. I'm now summing from n equal 1 to infinity. If I'm looking at the same ordering as before, but it is the exact same sequence. So yeah, find a series for the integral. If I integrate it term by term, I will get x plus 1/2 x squared plus x cubed over 3 times 2 factorial plus x to the 4th over 4 times 3 factorial plus x to the 5th over 5 times 4 factorial plus x to the 6th over 6 times 5 factorial and plus a constant. Now note, you can actually figure out that constant has to be 1 because if you plug in 0 for x, we know that has to be equal e to the 0, which is 1. So this constant has to be equal 1. So yeah, plus dot dot dot. And I guess you could show it from the work as well. If you start out with the sum n equals 0 to infinity of x to the n over n factorial. If you integrate, you'll get x to the n plus 1 over n plus 1 times n factorial. And now you get an extra term for the constant, so you'd be going from -1 to infinity. But note, that is just exactly the same as this, because that's n plus 1 factorial. You plug in -1, well, you're still starting from 0 on the bottom, well, you're still starting from 1 on the top. Alright, so if we look at e to the negative x, that is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, because every odd power it'll keep the negative, every even power it'll cancel it out, 4 factorial minus x to the 5th over 5 factorial, which would be the sum n equals 0 to infinity of -1 to the 0, yep, to the n I mean, times x to the n over n factorial. And then they want to multiply the series for e to the x and e to the negative x to find the first 6 terms of a series for e to the negative x. Okay, so we know then from our term-by-term multiplication theorem that when we're doing a multiplication of two sums, that their coefficients are the sum k equals 0 up to n of a sub n, a sub k, b sub k minus n minus k, n minus k. Yeah, that makes sense. So, our first term, so c sub 0, would just be, well, 0 up to 0. So one term of a sub 0, b sub 0. Well, that's easy. 1 times 1 is 1. So, next one, c sub 1. Well, that would be starting at 0 up to 1. So that would be at k equals 0, we'd have a sub 0, b sub 1, and then plus a sub 1, b sub 0. So that would be 1. Now, this is our a and this is our b. 1 times negative x. And then x times 1. So that's 0. So there is no 1 term. So plus 0 plus c sub 2. This would be a sub 0, b sub 2, plus a sub 1, b sub 1, plus a sub 2, b sub 0. So that would be the coefficients, not the terms. I get confused, but regardless, I don't really need to include the x, but it still would have been -1 plus 1. C sub 2 would be, so the first times the third, so e to the x times 1 over 2 factorial, so 1 over 2 factorial, plus the middles times each other, so 1 times -1 minus 1, and then add the next one, so plus, then it'll be a sub 2, that, times the 1, so plus 1 over 2 factorial. Well, that's going to be 1/2 plus 1/2 minus 1, so that's 0. I think you may see where this is going, but you can see what we'd expect. You'd expect when you multiply e to the x times e to the negative x, that's e to the 0, which is just 1. So this is the only term we're going to get. But yeah, you keep doing it. So the next one would be 1 over 3 factorial plus times 1 plus 1 over 2 factorial times 1. That'd be minus, wouldn't it be? Yeah. Plus 1 over 2 factorial times 1 minus 1 over 3 factorial. Yep, all goes to 0. C4. Only 2 more to go, but honestly you can kind of see where it's going to go. 1 over 4 factorial times 1. And then the next one would be 1 times negative, so minus 1 over 3 factorial. And then this one, 1 over 2 factorial times 1 over 2 factorial. Plus Yep. 1 over 2 factorial. Then minus, I believe. So now we'd be to 3 factorial times 1, so minus 1 over 3 factorial. And then we'd be at the 4 factorial times the 1, so plus 1 over 4 factorial, which would be, let's see, that's 1 over 24 minus 1 over 6 plus 1/2 minus 1 over 6 plus 1 over 24. So that's 1/24 plus 1/24 is 2/12. I mean, it's 2/24, which is 1/12. And then that's minus 1/3, so that's 2/6, plus 1/2. That doesn't seem like it's working out. 4 times 3 is 12, times 2 is 24. So 1. Yep, times that. 1 times that. 1 over 2 factorial times 1. Oh, 2 factorial squared. My bad. So that's 2 times 2, so that's 1/4. All right, so that's more like it. So that's 1/12 minus 4/12 plus 3/12, and that is 0. One more. C5. So 1 times x to the 5th, so negative 1 over 5 factorial plus 1 times that one, so plus 1 over 4 factorial plus, or minus 1 over 2 factorial times 3 factorial, so 1 over 2 times 6 plus, going into this one, 1 over 2 times 6. Yep. Because 3 factorial is 6, 2 factorial is 1. And then 4 factorial, so minus 1 over 4 factorial times 1, and then plus 1 over 5 factorial. See, that one's easy. The odd ones are pretty easy because they seem to cancel out term by term. The even ones you actually have to calculate. Alright. So that's the series for it. Series just comes out to be 1. Next time, we will look at Taylor and Maclaurin series. Special cases of the power series. They're pretty neat in and of themselves. Then that'll be it for our look at sequences and series this semester. It's a neat topic. Sadly cut a little bit short. I'd really like to fit another 2 topics in this if I could, but it's the way the semester goes. See you next video.